Hello and welcome to this video on simple harmonic motion. Simple harmonic motion, if you've forgotten, is the repetitive motion of objects, such as pendulum or springs with masses attached that go back and forth over a repeated path. We call it simple because it ignores friction. We neglect the effects of friction to make it easily calculatable. The two most common examples are a pendulum, such as here, which will swing to the right and then back, or a block on a spring, which will, once compressed, stretch out, continue stretching, and then stop and start moving back this way. The important point here is that it repeats the motion over and over again. We have equations for both of these, but what we're going to look at today is how the energy transfers between them and how the position, velocity, and acceleration change. We'll start with the position because we have a direct equation for that. The equation for position as stated on the AP exam sheet is x equals a cosine 2 pi f times t, where f is the frequency, a is the amplitude, cosine is cosine, and t is the time. The position will vary with time, but let's take a look at how we got this, how it looks. If we take either representations, I'll typically talk about pendulums because they're easier to work with in the real world. Getting a frictionless pendulum is, or something close to it, it's fairly easy. Getting a frictionless block on a spring, less so, at least a horizontal one. If we start here and we say the equilibrium point is 0 and measure all of my distances in terms of distance from the equilibrium, I start at my maximum value here. After a period of time, I go to 0, and then I go to the opposite side. Now, it's tempting to draw a straight line, but I have to consider what the pattern looks like coming back. After the same amount of time that it took me to get from here to here, I end up back at the center. And then I will complete a single period and end back where I started. And then the pattern repeats. And this repeating pattern, moving up and down, is a cosine wave. We can see it here. Granted, my ability to draw cosine has never been the greatest. Case in point. But if we want to talk about the velocity or how fast it's going, what we want to talk about is how it changes with time. Because in the beginning, for a pendulum or for a spring, you have potential energy. Gravitational for a pendulum, elastic for a spring, but then it will translate to kinetic energy, meaning it starts moving. Now, gravitational potential energy is based on height. Elastic potential energy is based on how much the spring's pressed. But kinetic energy is the matter of motion. It's velocity. If it is moving, it would have kinetic energy. But if it's not moving, if there's no movement whatsoever, it would only have gravitational or elastic potential. In other words, at these endpoints, here and here, or here and here, there is no velocity. You start with no velocity whatsoever. Now, as time goes on, it'll start speeding up and moving to the right, so you'll get faster. Since this is our maximum value here, this is our largest positive value over here at the left, any movement to the right would be decreasing, so we would have a negative velocity. We had a very large negative velocity at the center point, but as we go on, as we leave this equilibrium point, our energy starts changing back into potential, gravitational for a pendulum or elastic for a spring, and my velocity goes back down to 0. Once it's done, it's going to start moving to the left towards the positive side of the values where we started, which means my velocity is going to increase, be positive, and it'll stop increasing once you reach the center and start slowing down, returning back to 0 at the initial, and then the process repeats itself. Now, in this case, we clearly have a velocity graph. We still clearly have a continuation of what we saw before. For those of you that have studied calculus at all, you'll recognize that this is a cosine graph and this is a negative sine graph with different amplitudes, but the same period of the graph, the same points. The period doesn't change. The amplitude might, but the period doesn't, because this velocity is derivative of this position. Strictly speaking, the amplitude of the velocity graph, if I was to take the full derivative, would not be this, but this a is a constant.
It's the amplitude of the velocity graph, but not necessarily the same a you had in the x. For a specific expression, a would be the a you have in the x expression times 2 pi times the frequency by chain rule. But the important part here is that the inside of the expression doesn't change, just the outside.
Whenever you would have a position of 0, your velocity is at its max. Whenever you have a velocity of 0, your gravitational position, potential energy is at its max. You prefer the amplitude, the position, displacement is at its max. But what about acceleration? Well, again, if we refer to calculus, we'll once again realize that the derivative would be the derivative, which, since it's the second order derivative, there would be a 2 pi f squared multiplied on top of it. But again, the period hasn't changed, and it's just going to be an inverse cosine graph. So my acceleration in the beginning is going to be very large, and then it's going to taper off, hitting 0 right at the center when the velocity is at its largest, there's no change in my acceleration, and then it's going to start slowing down as it approaches the other side until eventually it'll hit a stopping point here and turn around. Again, noticing where these changing points are. So what we can clearly see is two things. Number one, as the position changes, so does the velocity, so does the acceleration, but they can all be predicted using sine, cosine, and its derivatives. Number two, when the position is at its largest, so is the acceleration, just opposite directions. If this is the largest positive value, the acceleration will be the largest negative. But the velocity is going to be 0 whenever your position or acceleration is at its max. This repetitive process, this repetition of patterns, is the essence of harmonic motion. It repeats. We can see the patterns. We can even go a step further because the EG and the EK will change based on these things. The position is directly related to how high the pendulum is or how stretched the spring is, which will directly impact potential energy. This kinetic energy is directly related to how fast it's going, and the acceleration is directly proportional to the force. In fact, I can take each of these graphs, copy them over to these graphs, and just change the labels. Now, there would be a multiplier in each of these cases. But the position graph is going to be the same general shape with different amplitudes as the potential energy. The kinetic energy is going to be the same general shape. Again, multipliers, and because it's velocity squared, it would be the squared cosine as opposed to the regular, as the velocity graph. And the acceleration is the net force, the force driving it, in this case gravity here, or gravity or tension here. The combination of gravity and tension here, but spring force here is going to be directly proportional to the acceleration because force equals mass times acceleration. And so we can see how the patterns that we see for position, velocity, and acceleration directly carry over to potential energy, kinetic energy, and normal force. And by knowing where any one of these are at, you can make inferences about the rest in simple harmonic motion. Anyways, thanks for watching. Have a good one.